Okay, so as per the previous class, we talked about the design for test. We are going to continue on design for testability techniques. So if you remember the last class, you were doing the stuck at fault. So I believe you know how stuck at fault works and what does it mean by stuck at fault and what is the use of this design for test. Okay, so today we're going to talk about this testable logic structures, and the model that we are going to study is called the Reedmuller circuits. So as testability is a measure of the cost of performing the following test activity, so it is very important to actually measure the cost for testing, from test pattern generation on how to how we apply the test pattern and then to where we analyze the test response after coming out from the test. So in this testable logic structure, Reedmuller circuit, it is actually an approach to design for test, DFT, that is based on implementing a logical function using a circuit structure which can be easily tested. The Reedmuller form of implementation is such a structure for two reasons. The circuit can be tested using a universal test set, so it reduces the test pattern generation cost. So we'll talk about the universal test set at the end of this lecture. And then the universal test set can be easily generated using compact hardware, so we actually can reduce the test pattern application cost. So Reedmuller circuit is made out of two types of logic gates. Mainly, it is this AND gate and XOR gate. So no other types of gates are required in Reedmuller circuits. So when we talk about Reedmuller circuits, our intention is to convert our existing logic gates or existing combi logic in the form of AND gate and XOR gate so that we can make the test pattern test the combi logic circuit. So let's look at the stuck at fault that we have discussed earlier here in the class. So if you remember, for AND gate, in order to test the stuck at fault, so let's say stuck at 0, in order to catch the stuck at 0, our input, the other input has to be 1. So when you have 1 and you have another input that is stuck at 0, your output will give you 0, even though if you input 1 into it. That's how you catch the stuck at 0 fault. So there's actually a pattern that you can look at the truth table here. So this is the AND gate truth table. If you look carefully, we fix this input A at 1. If B is 0, your output will toggle. If B is 1, your output will toggle to 1. It's like a mirror of the input B. So in an AND gate, we only look at the input 1, okay, to test the stuck at fault, regardless of stuck at fault at 1 or stuck at fault at 0. So you may refer back to your notes to understand the basic of this. So you can easily see the pattern of it. For AND gate, the input is 1 to catch stuck at fault. Okay, so let's look at the OR gate. So OR gate actually has the same characteristic. You can look back at your previous notes. So in order to catch the stuck at fault for OR gate, we have to fix the other side, tie the other side of the input to 0. So when it is 0, the other input is 0, you'll get 0. The other input is 1, you'll get 1. So if it's stuck at 1, then even if you input 0, you will still get 0. And if it's stuck at 0, if you input 1, it will still give you 0. So this is how you the stuck at fault and the test pattern to test the stuck at fault for OR gate. So XOR, on the other hand, okay, so let's look at this, the input for XOR and the output for XOR. So if you can see the pattern for XOR, it is called as, on the earlier slide, it is called as a universal test gate. That is because you look at this pattern here. When input A is 0, you can see the pattern of the transition at the output, and same goes to 1. So if both inputs are, if the input is tied to 1, you toggle the other side of the input, you'll still get a transition at the output, you still get a toggle value. So that is why it is known as universal, because it can propagate fault at any condition. So if you want to test stuck at fault for an XOR gate, you can tie input the other side of input to 0 or the other side of input to 1. It will all allow you to test a stuck at fault. You can do a quick write-up on your paper right now to know how this stuck at fault will work for XOR gate. Okay, so Reedmuller focused on using the XOR gate, converting your combi logic into XOR gate and AND gate. Okay, so you may ask why AND gate and XOR gate? Why not AND gate or OR gate, or just XOR gate by itself? So you can try it on any combi logic. Okay, combi logic cannot be converted with just XOR gate by itself. You need to use XOR gate and an AND gate to make the circuit, okay, to restructure the circuit, to convert the circuit, or to make the test pattern for the circuit. So from here, you just need to use the AND gate and the XOR gate to test to make the Reedmuller circuit. So we'll go to the next slide to understand more about it. So right here, this one, test property of XOR and AND gate. So it actually explains what I have explained earlier here. So when we do this Reedmuller, we don't need inverters. So with all the inputs to logic 1 guarantees that all product terms are high, this will ease the testing for stuck at 0 fault. So stuck at 1 fault can be tested by setting the input to 0, one input to 0 with the remaining inputs at logic 1. So XOR gate has no dominant value. This means that a fault sensitive value will pass through an XOR gate regardless of the state of the other input. So this means this part, regardless of the other side of input, the fault will pass through. So this is an example of how a general Reedmuller circuit looks like. So we are going to convert a combi logic, okay, from the circuit, from the combi logic circuit itself, we convert it into a Reedmuller circuit. And these this min terms and pi terms will explain to you how exactly we use this sum of products to convert the corresponding circuit into the AND gate and XOR gate. So you can read through quickly on this one. This is more of FYI for you. Okay, so now we are going to talk in depth of this triangular method of transformation. So this is the SOP sum of product to Reedmuller transformation. This is the triangular method, which is an easier method of transformation to do the conversion or transformation for a circuit to Reedmuller circuit. Okay, so consider the following example. This is the combi logic or the Boolean expression for your combi logic gates that you have that you need to convert into the Reedmuller circuit. So this is actually the sum of products of your combi logic. So taking A as the most significant bit, the MSB of the circuit. So A, MSB, C is MSB. Same goes to this, and this. Okay, so we are going to convert this Boolean expression into the coefficient. So MSB, LSB. So for this one, A is 0, B is 0, C is 1. So this this binary will give you 0, 0, 1. And for B, for the second term, A 0, B 1, C 0, 0, 1, 0. And this is 1, 0, 0, and this is 1, 1, 1. So we are going to take this into coefficient form. So F is the sum of 1, 0, 1, 0 is 2, 1, 0, 0 is 4, and 1, 1, 1 is 7, right? So because there are only 3 inputs, so the maximum the maximum value, the highest value of a 3 input can only give you 7, right? So from here we need to build out from D0 to D7. So D0 stands for the decimal of the total of D stands for the decimal of your coefficient of this circuit. So ABC, as I mentioned earlier, 3 inputs, so the decimal is 7. So if let's say your input is ABCD, then it will be 15. Okay, so right here, since we only have ABC, then we will have 7, decimal of 7. So we write out here D0 to D7. Okay, to represent this is to represent the coefficient that we have in the sum of product of this Boolean expression. So let's look at very carefully. We only have the sum of 1, 2, 4, and 7, right? So we will label this is D0, this is D1, D2, D3, D4, all the way to D7. So D0 is 0 because there's no term for D0, right? So we only have the sum for 1, 2, 4, 7. So 1 will label 1, 2 will label 2, 4 will label 4, and 7 will label 7. So we get the sum of 1, 2, 4, 7. Okay, so this is how we work out the D0 to D7. for this triangular method of transformation. So if let's say you have input of ABCD, then it should go from D0 all the way to D15, and then you label accordingly to your terms that you have in the Boolean expression. Alright, so you make out the first line of it. The next thing you're gonna do is to work out the triangle. So this is how we're gonna work out the triangle. We are going to look at every triangular sum. Okay, so let's look at here the first row, the second row. Okay, let's look at only the second row. We will go very slowly to help you understand. Okay, second row. Second row is the sum of the first row. So this is how it works. 0, 1, sum will give you 1. 1, 1, sum will give you 1, 0, but we only take at the last, we'll only take the last value. So 1, 1 will give you 0. Okay, so that is why it is an it's okay, we'll continue from here. So 1, 1 will give you 1, 0, but we'll take the last one, so it's 0. So 1, 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1. So in short, it's actually this. If you look carefully at it, it's actually an XOR gate. Okay. The different input will give you 1, the same input will give you 0. But to ease your understanding, you can also assume that this is the plus. Okay, the addition 0, 1 will give you 1, 1, 1. It is 1, 0, but we'll take the last one. So it's overflow, so it will be 0. Okay, so let's look at the third row. 1, 0 is 1. 1 plus 0 is 1. 0, 1 is 1. 1, 1 is 0. 1, 1 again, 0. 1, 0 is 1. 0, 1 is 1. Okay. Then the fourth row. 1 plus 1 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0. So we are going to repeat the whole, the whole triangular addition all the way until only you get one value. Okay, so it should have also 8 numbers from here all the way down. Okay, because we have this 3 inputs. Okay, so the coefficient here is actually the output. We'll call C0 to C7. This is how you label it. Okay, D0, D7, D0, D7 to D7 is your input. C0 to C7 is your output. Okay, so each pair of values is exclusive OR to generate the entry on the line below. So this is to explain to you the XOR of how it works to the next line, the next row. Okay, so once we work out the whole triangular, we will get the output, the coefficient for the output, which is C0 to C7. So now we're going to label those that we have 1. Okay, we'll only look at those that we have 1. Right here, C1 is 1, C2 is 1, and C4 is 1. Right? C1, C2, C4 is 1. So we are going to convert these coefficients back in the input form. Okay, what does that mean by this? We'll look at the next slide.
now that we have got the coefficient, the output coefficients, C1, C2, and C4 is 1. Okay? You can work out on the map of labeling it, or another easier way of doing this without using the map is to directly look at the coefficient by itself. So sorry, I missed out one important label over here. Let me add very quickly to it. So